What if every thought had mass? Imagine that every idea, every memory, every fleeting worry you have ever had adds a tiny, almost imperceptible weight to you. This is not just a metaphor for emotional burden, it is a genuine question at the very edge of physics, where the abstract world of information collides with the concrete reality of matter and energy. The question forces us to reconsider what we mean by physical. Is information just a ghost in the machine, an abstract pattern with no substance? Or does it have a physical footprint, a real, measurable presence in our universe? The answer could change how we see everything, from the human brain to the cosmos itself. The core idea linking information to the physical world is known as Landauer's principle. It was proposed by the physicist Rolf Landauer in 1961, and its conclusion is both simple and revolutionary. Landauer stated that any logically irreversible manipulation of information, such as erasing a bit of data, must be accompanied by a corresponding increase in the entropy of the environment. In simpler terms, to forget something to erase a bit from a computer's memory, you must pay a physical price. That price comes in the form of energy which is dissipated as a tiny puff of heat. It is an unavoidable cosmic tax on forgetting. Think of a computer bit as a tiny switch that can be in one of two positions, on-off, representing a 1, representing a 0 erasing. This bit means resetting it to a known state, say 0, regardless of its previous state. Now that we have established a link between information energy mass, we can ask a very practical question. How much does information actually weigh? Let's perform a simple back-of-the-envelope calculation. According to Landauer's principle, the minimum energy required to erase one bit of information is a very specific, very small number determined by the temperature of the system. At room temperature, this energy cost is incredibly tiny, about 3 times 10 to the minus 21 joules. Hard to grasp in everyday terms. Using Einstein's E equals mc squared, we can convert that energy into a mass. We simply divide the energy by the speed of light squared, c squared, a very large number. When you do the math, the result is astonishingly small. The mass of a single bit of information at room temperature comes out to be around 3 times 10 to the minus 38 kilograms. To put that number into perspective, a single electron, one of the lightest fundamental particles we know, has a mass of about 10 to the minus 30 kilograms. This means a single bit of information weighs less than 1/10,000,000th of the mass of a single electron. Let's scale this up to something more familiar, like a digital book. A typical e-book might contain about 4 megabits of information. If we multiply the mass of 1 bit by 4 million, the total mass of all the information in that book is still unimaginably small, on the order of 10 to the minus 31 kilograms. While the mass of a single thought or file is negligible, what happens when we consider information on a cosmic scale? The universe is filled with information. Every star, every planet, every particle interaction creates and processes information. The entire internet is a colossal repository of data that grows every second. Could the cumulative mass of all this information become significant? Could a sufficiently dense collection of data, a data center of the gods, actually become so massive that it collapses under its own gravity to form a black hole? The formation of a black hole depends on a critical threshold known as the Schwarzschild radius. For any given mass, if you can compress it into a sphere smaller than its Schwarzschild radius, its own gravity will become so overwhelmingly strong that nothing, not even light, can escape. For Earth, this radius is about the size of a marble. For the Sun, it is about 3 kilometers. The question then is whether a concentration of pure information could ever have enough mass energy to cross this threshold. If digital data has mass, then the same must be true for the information stored in our own brains. Every memory you form, every skill you learn, every fact you memorize is encoded in the physical structure and chemical state of your neurons. This biological information, like its digital counterpart, represents a certain amount of energy, and therefore a corresponding amount of mass. Does this mean that the act of thinking, learning, and remembering could literally increase your body weight? The answer, in principle, is yes. But the effect is, once again, profoundly subtle and hidden within the brain's complex biology. Your brain is a biological computer of staggering complexity, with approximately 86 billion neurons connected by trillions of synapses. Information is stored in the strength of these synaptic connections and the firing patterns of neural circuits. When you learn something new, these connections are physically altered. The connection between information and energy is not just about mass, It is deeply tied to the second law of thermodynamics, one of the most fundamental rules of the cosmos. This law states that the total entropy, or disorder, of a closed system can never decrease. Things tend to become more random and chaotic over time. Landauer's principle, the idea that erasing information must release heat, is a direct consequence of this law. To erase a bit is to reduce uncertainty and create order within a small system. The memory chip. The second law demands you pay for this by creating even more disorder elsewhere. Waste heat. This paints the universe as a grand accounting system. Every time a calculation is performed, every time a memory is wiped, a tiny energetic price is paid. Your brain, while thinking, is constantly processing and discarding information. While the idea that information has mass is a direct consequence of well-established physics, it is important to approach the topic with scientific humility and acknowledge the counter-arguments. The primary objection is not that the physics is wrong, but that its application to information can be misleading. The mass we are calculating is not inherent to the abstract bits themselves, but to the energy difference between the physical states used to represent them. The information is not a new type of particle. It is a property of the arrangement of existing particles. However, it is theoretically possible to design reversible computers that do not erase information, but instead shuffle it around, performing calculations without any minimum energy cost or heat dissipation. Many physicists believe a deeper theory of quantum gravity could reveal a more complex relationship between spacetime, matter, and information. The mass of all the data on the internet today is estimated to be less than the mass of a single grain of sand. The calculations offer a glimpse of unity and the limits of our knowledge.